Are whales talking to each other?
Definitely.
Where researchers at Project CETI are using artificial intelligence to decode the clicks.
We never saw this day coming. For the longest, humans have prided themselves as the most intelligent creators alive, but that just changed. Just recently, scientists have made a stunning breakthrough after a 20-minute interaction with a humpback whale. An AI system just finished analyzing 9,000 recordings of sperm whales. What it uncovered wasn't random noise, not even close. It found structure, a kind of phonetic alphabet, complete with vowel-like sounds that look strikingly similar to the basic building blocks of human speech. Join us in this video as we find out what AI finally decoded about whale language. The decoding process. For decades, scientists believed they understood sperm-whale communication. The consensus was simple. Whales used about 21 different click patterns, known as coders. Each coder was thought to carry a fixed, basic meaning, a warning, a signal, a way to stay in contact. Nothing complex, nothing language-like. Researchers treated it almost like a traffic light system. Limited signals, predictable meanings, no real depth. But that assumption, it didn't just turn out to be wrong, it collapsed completely. What scientists were actually looking at was something far richer. Long sequences made up of smaller building blocks, like an alphabet. These coders weren't just signals. In some ways, they functioned more like the vowels in human speech. And that realization changed everything. It was a normal day, and marine biologist David Gruber was sitting at Harvard's Radcliffe Institute, listening to old sperm whale recordings he had collected while studying jellyfish in the Caribbean. The sounds were familiar, rapid bursts of clicking, like underwater Morse code. He had heard them countless times before, just background noise. Or so he thought. One day, an MIT cryptographer, Shafi Goldwasser, walked past David Gruber's office. His door was open. She paused, listened for a moment, then said something that would change everything. "That sounds like Morse code. Have you tried using machine learning to decode it?" Gruber hadn't. In fact, no one had. Goldwasser wasn't just making a casual comment. She had spent her career breaking encrypted systems, the kind governments use to protect state secrets. So when she heard those whale clicks, she didn't hear random noise. She heard structure. To her, those sounds felt like a hidden code, one that simply hadn't been decoded yet. That single conversation pulled in another key figure, Michael Bronstein, an expert in artificial intelligence. He pointed out something powerful, that the same deep learning technology behind tools like ChatGPT could, in theory, be used to understand animal communication if enough data could be gathered. That idea sparked something much bigger. Over the next 5 years, a diverse team came together. AI experts, roboticists, linguists, and marine biologists, all working toward one bold goal: to communicate with another species. They went all in. They collected more recordings than any scientist ever had. They gathered richer behavioral data than any previous whale study. And they used more computing power than any marine biology project before it. By 2020, this effort officially became Project CETI, funded by the TED Audacious Project, and supported by institutions like Massachusetts Institute of Technology, Harvard University, and University of California, Berkeley, along with many others. The team set up a permanent research station in Dominica, a place where generations of sperm whale families have been studied for decades. These weren't just random animals. Researchers knew them. Individual whales had names, family lines were tracked, matriarchs were identified, social structures had been carefully mapped over years of observation, and the whales kept coming back, year after year, to the same waters. But the team didn't stop there. How far were they willing to search? What daredevil efforts did they put into the project? Keep watching to find out. How far they went and what they found. They pushed beyond anything done before in whale research. Advanced equipment was installed, including underwater microphone systems and hydrophone arrays placed along migration routes to capture their communication in unprecedented detail. For the first time, scientists weren't just listening, they were preparing to understand. Researchers took things even further. They attached small, non-invasive tags directly to the whales using suction cups. Each tag carried 3 synchronized microphones, powerful enough to separate individual voices within a group conversation. But it didn't stop there. These devices also tracked location through GPS, measured depth, and used accelerometers to monitor body movement with incredible precision, down to tiny shifts in angle. In other words, the system wasn't just recording sounds, it was capturing context. Who was speaking, who they were speaking to, what they were doing physically at that exact moment, and what the surrounding acoustic environment looked like. Every possible clue that could help explain meaning was recorded, all at the same time. That was the goal from the very beginning, not just to hear whale communication, but to understand it. Then came the data, 9,000 recordings, analyzed using the same kind of deep learning systems that power modern AI language tools. And what researchers heard was unexpected. These weren't the long melodic whale songs people are used to. Instead, they sounded more like bursts of digital data, fast, structured, almost mechanical. Then came the real shock. The eye didn't find 21 coders, as scientists had long believed. It found 156. But even that wasn't the biggest discovery. What truly mattered was what was inside those coders. Each one had internal structure, subtle changes in timing, rhythm shifts, and additional clicks layered in repeating patterns. These weren't random or decorative, they had a purpose. They functioned like phonemes, the smallest units of sound in human language. On their own, they don't mean much, but when combined according to certain rules, they create meaning. That changes everything, because it means whales aren't just sending fixed signals, like choosing from a menu. They're building messages, dynamically, using a modular system, very similar to how human language works. Think of it this way. English creates millions of words from just 44 basic sounds. Remove even one sound, and thousands of words disappear. Add new rules for combining sounds, and suddenly new words become possible. Sperm whales appear to follow the same principle. A limited set of sounds used to create an almost limitless range of expression. The basic building blocks are clicks, but the structure? That's where it gets astonishing. There's grammar, there are rules, and together they form a vast communication system that scientists are only just beginning to understand. Danielle Rouse summed it up simply when speaking to reporters. Our results show there is much more complexity here than previously believed. This is challenging what we thought we knew about the animal world. But honestly, that barely captures it. What the AI uncovered wasn't a small update to existing knowledge. It was a complete reset, a collapse of the long-held belief that no other species had developed anything close to the structure of human language, and yet something had. For millions of years deep in the ocean, in near total darkness, sperm whales had been using a system strikingly similar to language, quietly, unnoticed, for around 30 million years. Then came another discovery, one that left researchers stunned. A linguist at University of California, Berkeley, Gaspar Bakos, approached the data differently. Instead of analyzing patterns across sequences, he zoomed in, examining the tiniest acoustic details of individual clicks using advanced phonetic tools. What he found shook the foundations of linguistics. The whales weren't just making clicks, they were producing sounds that closely resemble human vowels. The R sound, like in father, the E sound, like in see, even diphthongs, those blended vowel sounds like oi in boy. This wasn't random, it was consistent, structured, meaningful. What did this discovery mean to the world of science and even linguistics? Let's see. I finally decoded whale language. As Bakos explained, this revealed an entirely new layer of complexity in their communication system. And here's why that matters so much. Vowels aren't simple sounds. They require precise control of frequency, something that, in humans, depends on specialized vocal anatomy, coordinated muscles, and the brain's ability to control them intentionally. For a long time, scientists believed that combination was uniquely human, shaped by our specific evolutionary path, environment, and biology. But now, that assumption is no longer safe, because deep beneath the ocean's surface, under crushing pressure and in total darkness, another species appears to have developed something remarkably similar, on its own. Gaspar Bakos explained the discovery in simple terms. In the past, researchers thought whale communication worked like Morse code, but this shows their calls are more like very, very slow vowels. That might sound subtle, but it isn't. It suggests a level of complexity that begins to approach human language. And that's extraordinary, because we're not talking about a species that shares a recent evolutionary path with us. Sperm whales developed their communication system in a completely different world, one shaped by darkness, pressure, and sound. Their last common ancestor with humans goes back hundreds of millions of years. Now, think about what this really means. Human speech didn't just appear overnight. Our vocal system evolved over millions of years. Our lowered larynx, flexible tongue, and fine control of airflow, all shaped specifically for producing speech, sounds like vowels. We evolved toward language. Sperm whales didn't. They started from something entirely different: echolocation clicks used for navigation and hunting in the deep ocean, where survival depends on detecting the smallest acoustic details, and yet arrived at something that, when analyzed with modern tools, looks strikingly similar to vowel-based communication. That's not coincidence. That is convergent evolution. Two completely separate evolutionary paths leading to the same complex solution. And when that solution involves something as specific as vowels, it forces a deeper conclusion. Vowel-based communication may not be a human accident. It may be a fundamental feature of intelligence itself. For a long time, language was seen as one of the last clear boundaries between humans and the rest of the animal world. Vowels, phonemes, grammar, and context, all uniquely ours. But this discovery doesn't just blur that boundary. It erases the ground it stood on. And if this realization feels unsettling, you're not alone. Because for the researchers studying it, this was just the beginning. A conversation a mile beneath the ocean's surface. That's what researchers are beginning to see. And what's most striking is this: whales don't just have the building blocks of communication, they use them in context. And that difference is everything. David Gruber once described how he became fascinated by sperm whales after first hearing their sounds. To him, they didn't sound like anything familiar. They felt alien, like signals from another world, rising from the deepest parts of the ocean. But the real discovery came later. What was this next discovery about, and how defining has it been for the world of science? Keep watching to find out. Whales might have their own mind. The same whale can produce different coders depending on who it's speaking to, what was just said, and what's happening around it. In other words, the meaning changes with context. That's not a fixed signal system. That's pragmatic communication. It's flexible, responsive, real-time adjustment based on social situation, very similar to how humans naturally shift tone when speaking to a child versus a colleague, or soften language depending on the listener. Shane Giro has spent over a decade observing sperm whale families in Dominica. From the surface, he has watched interactions unfold that look surprisingly familiar. Mothers appear to hand off their calves to babysitters before diving to hunt. Whales exchange sequences of clicks that resemble conversational back and forth. Sometimes the exchanges last nearly an hour. Multiple whales speak, respond, and build on each other's contributions. There is timing, rhythm, turn-taking, and, interestingly, occasional overlap when two whales click at the same time, which seems socially acceptable in their groups, much like close humans sometimes talk over one another. But here's what makes it truly remarkable. To choose the right signal for the right whale at the right moment requires more than memory or sound control. It requires something deeper. It requires a theory of mind, the ability to understand that another individual has a perspective separate from your own, and to adjust your communication accordingly. For a long time, that ability was considered uniquely human. Now, that assumption is no longer so certain. Researchers studying sperm whales are now beginning to question old assumptions. They are no longer sure that the simple framing, basic signals with fixed meanings, holds up, because what they're seeing is far more complex. Within whale groups, there are dominant voices and quieter ones. There are exchanges that look like disagreements, and others that feel like reassurance. Some interactions happen only between specific individuals, while others involve the entire family group. And importantly, none of it is random. The communication is structured and organized around relationships. What happens at the surface is reflected in patterns below the water, in the acoustic data. Social structure and sound are tightly linked. And then there's the biology behind it all. Sperm whales have the largest brains of any animal on Earth, about 6 times the size of a human brain. They live in matriarchal family groups with deep, multi-generational bonds. Knowledge and traditions are passed down from grandmother to mother to calf over decades, even centuries. They coordinate complex deep water hunts in total darkness, across vast distances, where success depends on real-time coordination and shared awareness. Their communication plays a critical role in making that possible. As one researcher put it, there's likely far more meaning in their communication system than we currently understand. And that's the key point. These are not simple animals. They never were. The limitation was never in them. It was in our ability to listen closely enough. But there is an important distinction here. Structure is not meaning. And this is where scientific precision becomes essential. The eye has mapped grammar-like patterns. It has not translated a single word. It has identified phonetic building blocks. It has modeled combinatorial rules. It has catalogued vowel-like sounds. It has even profiled individual whales by their unique acoustic signatures. It has documented conversational patterns across years of interaction within family groups. All of this is real, verified, peer-reviewed. But one thing is still missing. And what could that be? Let's see. One element away from a whale civilization. That element is meaning. We still don't know what any of it actually says. What does a specific coda sequence represent? What changes when the pattern rises or falls in tempo? Those questions remain unanswered. And for now, the whales are still speaking in a language we can map, but not yet understand. What does it mean when a mother clicks long sequences toward her calf compared to when a matriarch speaks to the entire group? Right now, nobody knows. And that gap, that space between understanding the structure of a language and understanding what it actually means, is where the next phase of research begins. To unlock meaning, scientists need correlation. They need enough data to connect specific vocalizations with specific observable behaviors, matching what is said with what is happening in the real world at that exact moment. That's why next-generation Bollinger tags are so important. These devices record sound using 3 synchronized microphones, while also tracking depth, GPS location, body orientation, and even the acoustic activity of nearby whales at the same time. All of this data feeds into a growing behavioral archive, one that researchers are also comparing against decades of field observations. And when you step back, the scale becomes almost hard to comprehend. Sperm whales can live up to 70 years. A matriarch swimming in the ocean today may have been born before sonar technology even existed. She has spent her entire life communicating in a system that science has only recently begun to recognize as potentially language-like. Whatever she has expressed over those decades, knowledge, warnings, guidance, and social coordination, all of it happened in a communications system we could not yet read. Project CETI is not entering this world as a translator with a finished dictionary. It is entering as a student, learning the alphabet first, then slowly building meaning through one behavioral link at a time. With every hour of new recording, the dictionary becomes a little less empty. And that raises a bigger question. What if they're right? History suggests we've been wrong before. In the 1960s, researchers Roger Payne and Scott McVeigh demonstrated that humpback whales produce complex, evolving songs. Before that discovery, whales were widely seen as large but simple animals, ecologically important, yes, but not especially intelligent or cognitively rich. That assumption didn't hold for long, and it makes you wonder what assumptions about sperm whales might be next. That single discovery changed how the public saw whales forever. It helped spark the modern Save the Whales movement, influenced the creation of the Marine Mammal Protection Act, and played a role in pushing several whale species back from the brink of extinction. One breakthrough about whale intelligence didn't just add to science. It reshaped conservation law itself. Now imagine something even bigger. If sperm whales are not just producing songs or simple signals, but actually using a structured, language-like system with building blocks similar to vowels, phonemes, and grammar, then the implications go far beyond anything we've seen before. Shane Giro has pointed out why this framing matters so much. When people hear stories about whale grandmothers, close-knit families, or social bonds between neighbors, it resonates in a way abstract science often doesn't, because people protect what they feel connected to, and language creates connection. If the public begins to understand sperm whales not just as intelligent creatures, but as communicating beings that share information, remember events, and pass knowledge across generations like human cultures do, then everything changes. Each whale is no longer just an animal in the ocean. It becomes a member of a speaking community, and that changes how we define intelligence itself. Why? What elements of a whale's intelligence makes it even more extraordinary? Keep watching to find out. Scientists are still struggling to accept this. Some researchers suggest that these animals may be among the most cognitively advanced beings on Earth. Their brains contain highly specialized structures, like spindle cells, associated in humans with memory, emotion, decision-making, and complex social behavior. But the implications are not just scientific, they are moral, legal, political, because once you see whales as communicators, the threats they face take on a different meaning. Commercial whaling in the 20th century killed hundreds of thousands of sperm whales. Today, ship strikes still claim lives every year, and industrial noise from shipping and naval sonar fills the ocean with constant acoustic interference. If whales are truly communicating through structured systems, then that noise is not just pollution, it becomes a disruption of the conversation, interference in culture, a breakdown in communication across generations. And that raises a difficult question. What does it mean to damage the language of another intelligent species? Legal scholars are already beginning to explore that question, and the answers could reshape how we think about rights, protection, and life in the ocean itself. If sperm whales use language to discuss ideas, maintain relationships, and pass cultural knowledge across generations, then a difficult question emerges. Do they qualify for legal personhood? And if they do, what rights would that imply? Rights the law has never had to seriously confront before. For now, the AI is still running. The data keeps coming in, and researchers believe a day may come when someone looks at a screen and doesn't just see patterns, but meaning. Not structure alone, but actual words. And that raises the question no one is ready to answer. What has a matriarch been telling her family for 70 years? What did a mother whale say the first time a human ship passed overhead? What do these families talk about as the oceans change? Warming waters, disappearing prey, and the ever-present noise of ships that now fills every corner of the sea. These whales have lived through it all. The sperm whales in the Caribbean today have experienced an ocean transformed in real time. They have lost family members to ships they could hear but not avoid. They have endured an underwater world increasingly filled with industrial sound, noise that disrupts the very medium they depend on to communicate. And if they truly have language, and the evidence increasingly suggests something close to it, then they have not been silent through any of this. They have been talking about it, talking about us. That is the deeper weight of what Project CETI is trying to uncover. Not just an animal communication system, but a long-running perspective on Earth itself, one that has existed for tens of millions of years, observing the arrival of humans and the transformation of the oceans. To make this work transparent, Project CETI also aims to build an open scientific platform where data can be shared publicly, allowing researchers around the world to contribute to understanding what these signals actually mean. At this point, the pieces of the system are falling into place. The alphabet has been mapped, vowel-like structures identified, and patterns documented across years of recordings. But the message itself, the meaning, remains unknown. It may have been spoken 1 million times already, across millions of years, in a language we are only now beginning to recognize. We still don't know what it says. And maybe the most important question is not just what we will discover, but how it will change how we see them once we do. How is the whale this intelligent? Why did we never know until AI came on board? Let's see. The sperm whale. The sperm whale, also known as the cachalot, is the largest of all toothed whales, and in fact, the biggest toothed predator on Earth. It's the only living species in its genus and belongs to a small group of whales that also includes the pygmy and dwarf sperm whales. These whales live in oceans all around the world. They are pelagic animals, meaning they spend most of their lives in open water and they migrate seasonally to find food and to breed. Their social lives are fascinating. Females and younger males stay together in close-knit groups, while fully grown males usually live alone, only joining others during mating periods. Within these groups, females work together to protect and care for their young. They give birth only once every 4 to 20 years, and a calf may stay with its mother for over a decade. Adult sperm whales have very few natural threats, though young calves and weaker individuals can sometimes fall prey to orcas. A full-grown male sperm whale can reach about 16 meters in length, with its enormous head making up nearly 1/3 of its body. These whales are also incredible divers, capable of plunging as deep as 2,250 meters, making them one of the deepest diving mammals on Earth. They use echolocation, basically sound waves, to navigate and hunt in the dark depths, producing some of the loudest sounds of any animal. Even more remarkable, sperm whales have the largest brain of any creature on the planet, over 5 times heavier than a human brain. They can live for 70 years or more. Their massive heads contain a waxy substance called spermaceti, which is how the whale got its name. In the past, this substance was highly valued and widely used in oil lamps, candles, and machinery. Another rare material, ambergris, a waxy substance sometimes found in their digestive system, is still prized today, especially in the perfume industry. Because of their value, sperm whales were heavily hunted in the 19th century, a practice famously portrayed in the novel Moby Dick. Today, however, they are protected by international agreements, although they are still considered a vulnerable species. The name sperm whale actually comes from a shortened version of spermaceti whale. Early sailors mistakenly believed that a waxy substance found in the whale's head, called spermaceti, was its semen. In reality, it's a semi-liquid, wax-like material with completely different functions. Sperm whales are also known as cachalots. This name likely comes from an old French word meaning tooth or big teeth. Similar words can still be found in regional dialects, like caixao in Gascon. The exact origin isn't fully clear, though some experts think it may trace back to Vulgar Latin, possibly referring to sword hilts. The word cachalot made its way into English through French, but it likely came originally from Spanish or Portuguese, cachalote, which may itself be linked to a word meaning big head. This idea fits well, since sperm whales are famous for their enormous heads. Variations of the name also appear in other languages, including Russian. The whale's scientific name, Physeter macrocephalus, also reflects its features. Physeter comes from a Greek word meaning blowpipe or blowhole, which is a key feature of whales. The species name macrocephalus means big-headed, again highlighting one of its most noticeable traits. Another scientific name sometimes used for the sperm whale is catodon, meaning down tooth. This refers to the fact that sperm whales have visible teeth only in their lower jaw. There's also the name Australasianus, which was once used for sperm whales found in the southern hemisphere. The sperm whale belongs to a large group of mammals called Cetatiodactyla, which includes both whales and even-toed land animals, like deer and cows. Within this group, it is part of Cetacea, the branch that includes all whales, dolphins, and porpoises. Going further, it falls under Odontoceti, the category for all toothed whales and dolphins. What makes the sperm whale especially unique is that it's the only living species in its genus, Physeter, and part of the family Physateridae. However, it does have close relatives, the pygmy sperm whale and the dwarf sperm whale. These smaller whales are sometimes placed in the same family, but in other classification systems, they're grouped into a separate family called Cogidi. In some cases, both families are combined into a larger group known as Physeteroidea. The sperm whale was first scientifically described in 1738 by Swedish scientist Peter Artedi, based on reports of stranded whales in places like Orkney and the Netherlands. Later, in 1758, the famous naturalist Carl Linnaeus included the sperm whale in his groundbreaking book Systema Naturae. At the time, he actually listed 4 species under the genus Physeter. Over time, scientists realized that there is only one true species of sperm whale. However, there was long-standing confusion about its correct scientific name. 2 names, Physeter catodon and Physeter macrocephalus, were both used since Linnaeus had introduced them at the same time. For many years, P. catodon was the more commonly used name. But in 1974, 2 Dutch zoologists, Antonius M. Husson and Lipke Holthuis, argued that P. macrocephalus should be the correct name. Today, most scientists agree with this and use Physeter macrocephalus as the official name, while catodon is considered a secondary or outdated synonym. What do you think about the whale language AI just decoded? Do you think whales just trumped chimps in intelligence? Share your thoughts in the comments section below. Thank you for joining us as we explored the realities of the recently decoded whale language. We hope you found this video both interesting and informative. Don't forget to like and subscribe. Click the next video on your screen to explore more interesting discoveries. See you there.